let z1 and z2 be two distinct complex numbers. And let z equal, and they say it's 1 minus t times z1 plus t times z2, for some real number with t being between 0 and 1. And they say if the argument w denotes the principal argument of a non-zero complex number w then. And we know the argument is the angle of kind of the position vector specifying the complex number of the complex plane and the real axis. Let me just draw that. So if we do an argand diagram, this is the imaginary axis, and this is the real axis. If this is our complex number, if that is z, its argument, the argument of z is going to be this angle right over here. So phi is equal to the argument of z. That's all they're telling us in this second part. Now, let's go through each of these and see are true. And just to be clear, this is one of those problems where more than one of these choices might be correct. So let's see if they're true. So let's first figure out what the magnitude of z minus z1 is. So the magnitude of z minus z1 is going to be the magnitude of, so let me write, this is going to be the magnitude of, let's do the z part first. Let me write in the same colors. So if I would just focus on the z first, z is this thing up here. And let me distribute the z1. So it's z1 minus tz1 minus tz1, and then plus tzz2. Plus tzz2. And from that, we want to subtract z1. So from that, we want to subtract z1. So minus z1. And that cancel out. That and that cancel out. And let's see, we can factor out a t over here. So this is going to be equal to the magnitude of, let's factor out a t times z2 minus z1. z2 minus z1. So that is the magnitude of z minus z1, this first term over here. Let's figure out the magnitude of z minus z2. The magnitude of z minus, I'm going to color code it, z minus z2 is equal to the magnitude, well, z is just this thing up here. Let me just write it out. So it is 1 minus t times z1 plus t times z2. That's z. And from that, we want to subtract z2. So minus z2. So what can we do over here? We can take a t minus 1 out from here. We can factor out the z2 out of these two terms. So this is going to be equal to the magnitude of 1 minus t times z1. 1 minus t times z1. That's this term right over here. Plus, let me do it in another color, plus t minus 1 plus t minus 1 times z2 times z2. The magnitude of this part over here is this thing over there. Now let's see what happens when we add this thing to this thing. That's what choice A is doing. We're adding this thing to this thing. Let's see if we can simplify it. So this becomes the absolute value, or the magnitude of t times z2 minus z1 plus, I'll do the whole thing here in magenta, plus this thing over here. And this thing over here, actually, before I even write it out, how can we simplify that? We'll have a 1 minus t and a t minus 1. Well, I'll just write it out here, but I'm going to change it up a little bit. So this is equal to the magnitude of 1 minus t times z1. And so that I have a 1 minus t here, I'm just going to put a negative out front. So minus 1 minus t. I just swap them. Negative 1 minus t is the same thing as positive t minus 1, z2. And then this thing over here, since I have the 1 minus t out there, this becomes the magnitude of, I'm just factoring out the 1 minus t times z1 minus z2. z1 minus z2. So we have this thing. Let me copy and paste it. So copy and paste. We have this thing plus this thing. This is what this expression A has simplified to. Now let's see if we can simplify that even more. Let's see if we can simplify it even more. So t is just a scalar. t is just a scalar, and t is between 0 and 1. They told us that over here. T is between 0 and 1. So this is positive. This right here is a positive value. And then this right here is also going to be, a positive value. T is greater than 0, and it is less than 1. So this is also going to be a positive value. And these are just scalars. So this is going to be the same thing. These are just scaling the magnitude. So this is going to be the same thing. These are positive values. So this is going to be t times the absolute value. Actually, let me not skip a step. This is going to be the same thing as the absolute value of t times the absolute value of z2 minus z1, because this is just scaling it, plus the absolute value of 1 minus t, plus the absolute value of 1 minus t, times the absolute value of z1 minus z2. Now, let me be clear. The absolute value of z1 minus z2 is going to be equal to the absolute value of z2 minus z1. These vectors are just pointing in different directions, or these complex numbers. One is just the negative of the other, but their absolute values or their magnitudes are going to be the same. So let me write z2 minus z1, the absolute value of z2 minus z1 there. And the reason why I'm doing it is so I get the same thing here, and I can factor it out. So the absolute value of z2 minus z1 is the same thing as the absolute value of z1 minus z2, because it's just going in the other direction. Now, what can we do here? Well, the absolute value of t, remember, t is positive. So this is just going to be equal to t. The absolute value of 1 minus t, once again, that's positive, so that's just going to be 1 minus t. So we can factor this business out. So we're going to get t plus 1 minus t times the absolute value of z2 minus z1. z2 minus z1. Now, the t's cancel out here. We just got a 1 out front. So this is just equal to the absolute value of z2 minus z1. So we see that choice A does work. This plus this does indeed equal that. I'm going to leave you there. And in the next video, we're going to try out some of these other possibilities to see if they might also be true. In the last video, we saw that choice A is true. Now let's see if B, C, and D are also true. So choice B, they're telling us that the argument, let me rewrite it over here. I'll do it in another color. Choice B is telling us that the argument of z minus z1 is equal to the argument of z minus z2. Now let's think about this a little bit. We already did some work. We simplified what z minus z1 is equal to. It's equal to t times z2 minus z1. So this is equivalent to saying that the argument of t times z2 minus z1. I'm just leveraging some of the algebra that we already did, because this thing is the same thing as what's inside of the absolute value sign, which is the same thing as this thing over here. So the argument is t times z2 minus z1 is equal to, so I'm just rewriting statement B. Statement B is just saying that this should be equal to the argument of, now what's z minus z2? Z minus z2, we figured out was this thing over here. Actually, let's say it's this thing right over here. It's equal to this thing right over here. And we could rewrite this thing as being equal to, I'm running out of real estate here, but we could rewrite this thing right here as being equal to 1 minus t, as being equal to 1 minus t. I'm just factoring out the 1 minus t times z1 times z1 minus z2. z1 minus z2. Or, so that we can get it in the same form here, let's multiply this times -1 and this times -1. So I'm multiplying by -1 twice, so I'm not changing the number. So this is going to be equal to, or the statement is claiming this is equal to, the argument of t minus 1. Let me write it a little bit neater than that. So the claim is that this should be equal to the argument of t minus 1 times z2 minus z1. So let's think about this. And just remember, all I did here is I multiplied this by -1 and this by -1. If I multiply two things times -1, it's equivalent to multiplying by -1 twice, which is just multiplying it by 1. So I was able to swap both of these. So is this true? Is it true that the argument of t times z2 minus z1, is it true that that's the same thing as the argument of t minus 1 times z2 minus z1? So let's just think about it a little bit. Let's draw an argand diagram. Let's draw an argand diagram here. That's the imaginary axis. This is the real axis. And let's draw the vector z2 minus z1. So let's say that this right here is the vector. Let me draw it like this. This right here is the vector z2 minus z1. Now, what would t times z2 minus z1 look like? So t, we learned, is between 0 and 1. So it's going to be a scaled down version of z2 minus z1. So this right here, so who knows what it is? This right here would be t times z2 minus z1. Now, what would t minus 1 times z2 minus z1 look like? Well, t minus 1, remember, t is between 0 and 1. So t is less than 1. So t minus 1, this right here is going to be a negative number. It's going to be a negative number. So it's going to be, we're going to be scaling it by a negative number. So we're going to be scaling z2 minus z1 by a negative number. So this thing right over here, t minus 1 times z2 minus z1 is going to look like this. It's going to look like this. This is t minus 1 times z2 minus z1. Now, the arguments are just the angles between each of these numbers and the real axis. So the argument for this thing right over here is going to be this angle. It's going to be phi right over here. So I could call that phi. But what's the argument for this thing? It's going to be that plus pi, or plus 180 degrees. We have to go all the way around. So they are not the same angle. Whatever number this is right over here, this number is going to be that plus pi, or even minus pi. You could even go that way. But they're definitely not going to be the same angle. So we can cross out choice B as an option. But now that we're in this mode, let's see if we can tackle choice D, because it looks very similar. And then I'll probably do choice C in the next video, because I don't want to spend too much time in each video. So what is choice D telling us? Let me write it down here. Choice D is telling us, so we don't know, we have to see if it's true, that the argument of z minus z1 is equal to the argument of z2 minus z1. So let's think a little bit about this right now. So once again, they tell us, we already figured out what z minus z1 is equal to. It's equal to this business over here. So this statement is equivalent to the statement that the argument of z minus z1, which is t times z2 minus z1, leveraging our algebra in the last video, t times z2 minus z1, is this equal to the argument of z2 minus z1? Well, once again, let's draw our argand diagram here. We could even leverage, actually, we can leverage the same argand diagram. In green right here, we have z2 minus z1. Its argument would be this angle right over here. It would be this angle phi. This is z2 minus z1. That's that angle. T times z2 minus z1 is just going to be the scaled down version of it, what we have in orange. Now, clearly, this is just, t is positive, so it's not pointing in another direction. This is just a scaled down version of this. This vector and this vector, or this complex number and this complex number, are going to point in the same direction. So their angles are the same. Let me do it. This orange vector is this right over here, or that orange complex number is this right over here. This is t times z2 minus z1. And then the green one, just to be clear, z2 minus z1, is that. They're clearly in the same direction. They clearly have the same argument. So choice D is another correct choice. Now I'm going to leave you there. In the next video, we're going to see if choice C works. So we're in the home stretch. Let's see if part C is true. And I'm running out of real estate. So let me copy and paste it, actually. Actually, maybe I could do it over here to the left. I had some doodles here. Let me clear those out. So let's see if we can do it over here to the left. Part C. So we have this determinant, and it's claiming that it equals 0. So we have to see if that's true. And so we can actually try to multiply these out and see if anything interesting happens. But we could even better leverage some of the algebra that we've already done for part A. For part A. In part A, we figured out that z minus z1 is equal to t times z2 minus z1 is equal to t times z2 minus z1. So this thing right over here, this is the same thing as t times z2 minus z1. And the reason why that's interesting is I have a z2 minus z1 here. So I'm starting to have similar things. And then this thing over here, so if I take the conjugate of each of these, the conjugate of z minus the conjugate of z1, this is going to be equal to t times the conjugate of z2 minus the conjugate of z1. And I know that because when I do this, I'm swapping all of the signs on the imaginary parts of the complex numbers. So if you were to go through this entire process, just swapping the imaginary parts of the complex number, the end result would have its imaginary parts swapped. And that's exactly what we have over here. We have the imaginary parts swapped over here. So if you want to work it out, set this equal to a plus bi, or set this equal to a1 plus b1. You can work it out, but I think it's a pretty intuitive idea that we're just making all of the, we're just swapping the signs on all of the imaginary parts of each of these complex numbers. Now, with this said, this determinant becomes pretty simple. This becomes t times z2 minus z1. This becomes t times the conjugate of z2 minus z1. This down here is z2 minus z1. And then this over here is the conjugate of z2 minus z1. And so what is this determinant? It's going to be this times this. So it's t times z2 minus z1 times z2 minus z1 times the conjugate of those. So it's that times that minus this times this. So minus t z2 z2 minus z1 times the conjugate of z2 minus the conjugate of z1. Now, this is exactly equal to this. These things are obviously going to cancel out, and we're clearly going to get 0. So C is also true. So the correct answers to this original problem, the correct answers were A, C, and D. Let omega be a complex cube root of unity with omega not being equal to 1. A fair die is thrown 3 times. If r1, r2, and r3 are the numbers obtained on the die, then the probability that omega to the r1 plus omega to the r2 plus omega to the r3 equals 0 is. This is a fascinating problem. So let's just start with the first part and then see if some patterns fall into place for us to be able to tackle the second part. So omega is a complex cube root of unity, which is just a fancy way of saying it's a complex cube root of 1, with omega not being equal to 1. So let's just set up an equation here. Let's try to think about all of the cube roots. Let's just think about all of the cube roots of 1. So if we say that's analogous to figuring out all of the x's that satisfy x to the third is equal to 1. Or we can subtract 1 from both sides of this equation and write this as x to the third minus 1 is equal to 0. All of the roots of this equation right here will be cube roots of 1. They will satisfy this over here. And this is the same thing as I could write it over here. X is equal to the cube root of 1. These are all equivalent statements. So how do we do that? Well, we know what one of the roots are. We know that x equals 1 is a root. Or another way we can think about it, we know that x minus 1 is a factor here. We know that this can be factored as x minus 1 times something squared plus something x, some quadratic, let me write here, some quadratic right here is equal to 0. We can factor this. And to figure out what the quadratic is, we just have to do a little bit of polynomial, or I guess we could call it algebraic long division. We just have to divide x minus 1 into this, and then we'll get what this quadratic is. So let's do that. Let us divide x minus 1 into x to the third minus 1. And I'll do it in place. So this is the third degree place. X to the third, I'll leave space for the x squared place, leave space for the x to the first place, and then we have x to the 0, which is the ones place, so that's negative 1. So I just wrote x to the third minus 1, but I wrote it out this so I have space to kind of keep our counting pretty clean. So we just do algebraic long division here. So x minus 1 goes into x to the third minus 1. You just look at the highest degree terms. X goes into x to the third, x squared times. It goes x squared times x is x to the third. X squared times negative 1 is minus x squared. Now we want to subtract the magenta stuff from the orange stuff, or we could add the negative of it. So let's just multiply this times negative 1. So positive. Sorry, we're multiplying it times negative 1. So this is a negative, and then this will become a positive. We're just subtracting what I originally had written from that, but I just made it negative, and now we'll add. And so this will become, these cancel out. We get x squared minus x squared minus 1. Just algebraic long division. Once again, how many times does x minus 1 go into x squared minus 1? Look at the highest degree terms. X goes into x squared. I'll just arbitrarily switch colors. X goes into x squared x times. So this is plus x. X times x is x squared. X times negative 1 is negative x. Same drill. Subtract this from up there, or we could add the negative. So this becomes negative, this becomes positive. These guys cancel out. You get x. Bring this down, x minus 1. X minus 1 goes into x minus 1 exactly one time. It goes exactly one time. 1 times x minus 1 is x minus 1, and you get a remainder 0. So it divided evenly, which makes sense because this is one of the factors of that. We know that this is a root. So if we wanted to factor, if we want to completely factor this, we can write this as x minus 1 times this thing over here, times a quadratic, times x squared plus x plus 1 is equal to 0. So if we wanted to find the non-1 roots of this over here, we just have to find the roots of this thing right over here. Whatever the roots are this are going to make this expression equal to 0, which would make this entire expression equal to 0, make this entire expression equal to 0. So we just have to find this guy's roots. And I could already guess that they're going to be complex. So don't even attempt to factor it. You could attempt to factor it if you like, just by looking at it. But we're going to use a quadratic formula. So the roots here, the roots for this part, we say x is equal to negative b. B is 1. So negative 1 plus or minus the square root of b squared. B is 1. So 1 minus 4 times a times c. Well, a and c are both 1, so it's just minus 4. All of that over 2 times a. A is just 1, so all of that over 2. So x is equal to negative 1 plus or minus the square root of negative 3. And we were right. This is going to be a complex root over 2. Now, what's the square root of negative 3? We could write this square root of negative 3. This is the same thing as the square root of negative 1 times the square root of 3. And this we know from studying imaginary numbers and complex numbers. This is I. That right there is I. So the other roots, and there are 2 here because we're plus square root of negative 3 and subtracting the square root of negative 3. So the other roots here, x could be equal to negative 1 plus or minus the square root of 3 times I. And I'll put I here just so it's nice and clear. That's not a vector. It's just like that. I. All of that over 2. So what we just did so far is we now know all three roots of 1, especially if we're thinking about the complex roots. 1 is one of the roots. The other roots are negative 1 plus the square root of 3i over 2, and negative 1 minus the square root of 3i over 2. And so they're saying that omega is one of these two roots. We either take the positive or the negative, and it looks like it doesn't matter. It says let omega be a complex cube root of unity. So it could be either one of these. So let's just pick one of them. So let's just say omega is equal to -1 minus the square root of 3I minus the square root of 3I, and I'll just distribute the divided by 2. So we could call this, let me write it this way. It's -1/2 minus the square root of 3 over 2I. I'm just picking, once again, not a vector. My brain keeps wanting to put a little hat on top of it. It's not a vector. It's just an imaginary number. It's I. Well, this is actually a complex number because we have a real part and an imaginary part. So I'm just going to pick that to be my omega. It's one of the non-1 complex roots. Third roots, or I guess we could say, what was the actual wording they said? One of the cube roots, one of the complex cube roots of 1, of unity, that is not 1. So let's just let omega be equal to that. So this first statement can translate into this. And then a fair die is thrown 3 times. If R1, R2, R3 are the numbers obtained on the die, then the probability that omega to the R. So let's think about this a little bit. Let's think about because we're going to be taking omega to different powers. So let's think about what happens when we take this omega to different powers. So this right here is clearly omega to the first power, the way we've defined it. Let's think about what omega squared is. So omega squared is equal to -1/2 minus square root of 3 over 2I, and this will give us good practice multiplying complex numbers, times -1/2 minus times this, what's the same thing? We're squaring it. And so this is going to be equal to -1/2 times -1/2 is +1/4. And then you have -1/2 times -3/2I. The negatives cancel out. Or the square root of 3/2, I should say. So -1/2 times this is going to be positive square root of 3 over 4I. Then we can multiply this times this. It's going to give us the same thing as that. So the negatives cancel out. And so we have plus square root of 3 over 4I. And then we're going to want to multiply. And then we're going to want to multiply the two imaginary terms. So the negatives cancel out. And so you have square root of 3 times square root of 3, which is just 3. And then you have 2 times 2, which is 4. And then you have I times I, which is -1. So let me just put a -1. So times -1 over here. So let's simplify this. This gives us 1/4 plus square root of 3 over 4I plus square root of 3 over 4I. That's 2 square roots of 3 over 4I, or square root of, so that's the same thing as square root of 3 over 2I. And then minus 3/4. Minus 3/4. And we can simplify this even more. The real parts, we can add 1/4 minus 3/4 is -2/4 or -1/2. So this is -1/2 plus square root of 3 over 2I. So that's interesting. When I squared omega, I got another one of the cube roots, complex cube roots of 1. I actually got its conjugate. And if any of y'all who've studied complex analysis and think about the complex plane, it should be pretty clear why this happened. But if you don't worry too much about it. Now what I want to do is I want to take omega to the third power, just to really understand what's happening with omega. And if you studied complex analysis, this part would be quicker for you. You would know it. So what's omega to the third power? Omega to the third power is going to be omega squared times omega. Omega squared is just that right over there. We just calculated it. It's -1/2 plus square root of 3 over 2I. And we're going to have to multiply that times omega. Omega was the conjugate of this thing. So it's -1/2 minus. Conjugate just means opposite side on the complex part. So minus square root of 3 over 2I. That's what we defined omega to be right over here. This right over here is omega. That's omega. This right here is omega squared. So let's multiply these. So first, -1/2 times -1/2 gives us gives us +1/4. Have to be careful. This gives us 1/4. And then if we take -1/2, I shouldn't do it that way. Let's do -1/2 times negative square root of 3 over 2I. Negatives cancel out, so we get plus square root of 3. Let me make sure square root of 3 over 4I. And then we can multiply this times this. It gives us the same thing. So it gives us plus, let me make sure I'm doing this right. Oh, no, it's not going to give us the same thing. Now, 1 is negative, 1 is positive. So it's going to give us, be very careful. So negative 1/2 times positive square root of 3 over 2I is negative square root of 3 over 4I. And then finally, multiply the two imaginary parts. Multiply that. I don't want to use it. I want to use a different color. Multiply that times that. That gives us positive times a negative, gives us a negative. Square root of 3 times square root of 3 is 3. 2 times 2 is 4. I times I is negative 1. Or we can multiply the negative 1 times this negative over here, becomes a positive. So what do we get? These guys cancel out. We have 1/4 plus 3/4. It is equal to 1. It is equal to 1. So this is interesting. This is interesting over here. So omega is equal to this thing right over here. Omega squared is equal to its conjugate. Omega squared is equal to its conjugate right over here. We just swapped the sign over there. And then omega to the third is going to be equal to this thing. Is going to be equal to unity. Actually, we knew that. I shouldn't even have to worry about this. I don't know why I even went through that process. Well, it was good multiplying. We knew it was the cube root of unity. So we knew if we took it to the third power. So this was, to some degree, just a waste of time. But what does this tell us? So we now kind of understand what the different powers of omega. What will omega to the fourth power be? Well, it's going to be this times omega. So it's just going to be omega again. What's omega to the fifth power? It's going to be this. What's omega to the sixth power? It's going to be this again. So let's just use that, and we're going to tackle that in the next part of the problem in the next video. In the last video, we started on this problem right here, where we said, let omega be a complex cube root of unity, and omega cannot be equal to 1. And so we figured out what all of the complex cube roots of unity were. We figured out, well, we knew that 1 was one of them, and we used that to factor out this third degree equation right over here. And we figured out the other roots, cube roots of unity, were negative 1 plus or minus the square root of 3I over 2. And we said, look, the problem said let omega be one of the, or be a complex cube root of unity. So I just picked it to be the negative version. So I said let omega be this thing right over here. Now, and just to kind of explore the space a little bit, we said, okay, what's omega squared? And we figured out that it was actually the conjugate of this. It's the plus version of this. So we got omega squared right over here. And then I kind of wasted your time a little bit because we know what omega cubed is. We know that omega is a cube root of unity. So omega cubed must be unity, but it wasn't harmful, I guess, to go through the process. It shows you sometimes my brain gets into a rut and just does stuff that it doesn't have to do. But we figured out, we multiplied this times omega to show that, hey, it is definitely equal to 1. So what we're able to do is set up a situation, and we will use this to think about the next part of the problem. So omega is equal to negative 1/2, or maybe I should say omega to the first power is equal to negative 1/2 minus the square root of 3 over 2I. Omega to the second power, let me write it over here. Omega to the second power is equal to negative 1 plus the square root of 3 over 2I. And then omega to the third power, and that was pretty straightforward, is equal to 1. And I touched on this in the last video. What is omega to the fourth power? Omega to the fourth power is going to be omega to the third times omega. So it's going to be omega again. So this is also going to be, let me scroll to the left a little bit. This is also going to be omega to the fourth power. Omega to the fourth power is the same thing as omega to the first power, which is this. Now what's to the fifth power? Well, it's going to be omega times the fourth power. So it's omega times this. Well, omega times this is the same thing as omega squared, so it's going to be that. So this is omega to the fifth power. And what's omega to the sixth power? Well, that's just the same thing as taking omega cubed and squaring it. So this is also going to be 1. So this is omega to the sixth. Or you could just view it's this times omega, right? Because it's to the fifth power, and we saw that that's also equal to 1. So we did set up, and the reason why I went up to the sixth power is because if you remember the old problem, we're rolling a die. And on that die, I'm assuming it's a normal six-sided die, we're going to get values between 1 and 6. And we're going to take omega to the different powers, and we're going to see if it equals to 0. And we want to find the probability of this being equal to 0. So let me write this down. We want to find the probability. We want to find the probability that omega, and we're just using the omega that we picked because they said it's one of the complex roots that isn't 1. So we want to find the probability that omega to the first die of the roll plus omega to the second die of the roll plus omega to the third die of the roll, that when you take their sum, that is equal to 0. This is what we need to figure out. So to figure this out, let's just figure out what combinations of powers of omega will even add up to 0. How can we even add them up to 0? None of these, I mean, they all have to cancel out some way. And if you look at them, it looks pretty interesting of how they might cancel out. If I take one version of this, the only way that they really can cancel out is if I take one version of this and add it to this, and then add it to this. Let me show you. If I take negative 1 half minus square root of 3 over 2i, and I add it to this, negative 1 half plus square root of 3 over 2i, and then I add it to 1, and then I add it to this, and then I add it to this, what do I get? Well, you're going to have this guy and this guy are going to cancel out. Negative 1 half plus negative 1 half are going to be equal to negative 1. You add negative 1 to 1, it's going to be equal to 0. So essentially, what we're going to say, what it's asking us, what's the probability that I get for each of these terms, that I get one each of these powers of omega? Or another way of thinking about this, what's the probability? So if we think of it this way, so R1, let's think of it this way. R1 could be equal to, we could get, if we say that this is we're going to get omega here, we're going to get, which is the same thing as omega to the fourth power. So could be, R1 could be 1 or 4. R2, and this is in the situation where the first one gives us omega, the second one's omega squared, or the second one gives us this value, and then the third one gives us 1. So R2 would be 5 or 2. R2 would be 5 or 2, and then R3 would be equal to 3 or 6. 3 or 6. Now, I want to be very clear. We could swap these around. There's actually six ways that you could instead of this being the first roll, this roll could be 1 or 4, and then this one could be 5 or 2, and then this one could be 3 or 6. So there's actually 6 ways of doing this. I guess you could say you could permute these six different ways, or 3 times 2 times 1. But we'll think about that in a second. But let's just, assuming that we want this way, where this first one is going to evaluate to this, and the second one is going to evaluate to this, and the third one is going to evaluate to this. What's the probability of that happening? And then we're going to multiply that by 6, because there's 6 ways to rearrange these terms right over here. So let's do that. So what's the probability of that happening? Well, the probability that R1 is a 1 or a 4, well, that's 2 values out of 6, so the probability is 1/3 there. The probability that R2 is a 5 or a 2, well, that's also going to be 1/3. That's 2 values out of a possible of 6. The probability that R3 is a 3 or a 6, only 2 possibilities there. So 2 out of 6 possible faces of the die, so times 1/3. So the probability that this first one is going to evaluate, to this value right over here. The second one's going to evaluate to this value, and the third one's going to evaluate to 1, is going to be 1/3 times 1/3 times 1/3, which is 1 over 27. Now, and I touched on this already. There's 6 ways that you could rearrange this 6 ways. You have 3 terms, and you're putting them in 3 places. So in the first place, you could put 3 of the terms. In the second place, you have 2 terms left that you could put, and in the last place, you only have 1 term left. So there's 3 times 2 times 1 ways to arrange these things. We can arrange this 3 times 2 times 1 different ways. So there's 6 different arrangements. The probability of each is 1 over 27. So the probability under question, this thing over here, there's 6 arrangements. There's 6 arrangements of getting these things to be added up in this way, and the probability of each of them is 1 over 27. So it's equal to 6 over 27. And if you divide the numerator and the denominator by 3, it's equal to 2 over 9. And we're done. It wasn't too bad, I think. The probability of getting omega to the R1 plus omega to the R2 plus omega to the R3, where R1 and R2, R3 are numbers obtained from rolling a fair die. The probability that when you add all of these, it's going to be equal to 0 is 2 over 9. Anyway, I thought that was a pretty neat problem. Let a and b be two distinct points on the parabola y squared is equal to 4x. If the axis of the parabola touches a circle of radius r having AB as its diameter, then the slope of the line joining a and b can be. So let's draw this. So let me draw my axes here. That's my y-axis. And here is my x-axis. And then the parabola y squared is equal to 4x would look like this, something like that. That would be in the first quadrant, and then it would be symmetric around that. It would look like that. So this would be y squared is equal to 4x. Or if I just focused on this top part over here, I could take the principal root of both sides, and I would get y is equal to 2 times the square root of x, just taking the square root of both sides. This square root of 4x is 2 times the square root of x. This down here would be y is equal to negative 2 times the square root of x. So the positive square root, the negative square root of both sides. But this one defines this whole parabola implicitly. And then they tell us that if the axis of the parabola, that's essentially the x-axis in this drawing, if the axis of the parabola touches a circle of radius r having AB as its diameter. So let's take 2 points on this parabola. So let's say that is point A, and let's say that this is point B. It is the diameter for some circle. So that's the diameter for some circle that just touches this axis. So it'll just touch on here. So let me see how well I can draw that circle. Obviously, this will not be an exact drawing, but let me try my best to draw the circle under question. So the circle will look, I can do a better job than that. The circle will would look like that. That's my best shot at it. And then it has a radius r. So if we say the center of the circle, and obviously the diameter will go through the center of the circle, this distance right here is r. So another way to think about it, this y value right over here, that y value is r. Now, let's think a little bit about the center of this circle, because maybe with the center of the circle we can relate the a's and the b's to the r's. So let me define a and b. So let me define the point A. Let's say the point A, just for convenience, let's make x is equal to lowercase a squared. If x is lowercase a squared, then the square root of that is a times 2. Then y will be 2a. So this right here is the point a squared 2a. And let's make b the point using the same logic. Let's just say that's lowercase b squared. And I'm doing that so that when I take the square root, it'll become simple. So the square root of b squared is b times 2 is 2b. Now, let's get the coordinates for the center of that diameter. Now, the center of that diameter is just the midpoint of this point and that point. So let me write it down here. The midpoint of A and B, the points A and B, is going to be equal to the average of the x values, a squared plus b squared over 2, and the average of the y values. So this will be 2a plus 2b, all of that over 2. And of course, the 2's cancel out. And so this is going to be a plus b. That is the y value of the midpoint. So this point right over here is going to be a squared plus b squared over 2, comma, a plus b. Now, we just saw that this height right here is r. So a plus b, this y value right over here, is also equal to r. This is equal to a plus b. Right? The y value in between 2a and the y value in between 2b right over here. 2b. This is a plus b. So just like that, we were able to get a relationship between a, b, and r. So we know a plus b is equal to r. Now let's try to find the actual slope of this diameter. That's what they want to ask us. The slope of the line joining A and B can be. So let's figure out the slope of this actual line. And let's see if we can relate it to r in some way, maybe using this information. Because all the answers they give us are in terms of r. So we need to have an answer in terms of r. So the slope is going to be change in y over change in x. So 2a minus 2b, 2a minus 2b over a squared minus b squared, over a squared minus b squared. This is equal to 2 times a minus b over a plus b. This is just a difference of squares. A plus b times a minus b. The a minus b's cancel out. The slope of the diameter, the slope of the line that we care about, is going to be, it's going to be 2 over a plus b. It's 2 over a plus b. Now, that's clearly not one of the answers. We need our answer in terms of r. But we just figured out the y-coordinate of the midpoint, which was a plus b. That is equal to r. So this is the same thing as 2 over r. So the slope of this line right over here, the slope of this line is 2 over r. 2 over r. Now, you might be tempted to say, okay, the answer is C. But, and I actually probably should have told you this at the beginning of this video in case you wanted to pause it and try it yourself, is that this is actually a multiple correct answer problem. So you can actually have multiple choices here. So we want to make sure that this isn't the only answer. And it's not the only answer, because we could have put A here and B here and drawn the circle like this, and drawn the circle, essentially the exact same circle, but in the fourth quadrant. So I could have drawn the circle like this, and then I would have been dealing with the slope of this diameter would be in question. And you can see everything is symmetric. It's just flipped around the axis of symmetry. It's flipped around the x-axis. Whatever is the slope up here, the negative of it is going to be the slope over here. So this is also a potential slope. So if this is 2 over r, then this slope over here is negative 2 over r. So this is also an option. And just based on the reasoning we just did, you could have ruled out 2 of these. If you knew that this slope is a, or if you know that this slope up here is going to be, I don't know, if this slope up here was going to be r, then this slope over here is going to be negative r. If this slope up here is going to be a plus b, the slope would be negative a plus b. So you know that you would have to have 2 answers that are the negative of each other. So when you look at just the choices, you could have said, oh, it's either going to be a and b because they're the negatives of each other, or it's going to be C and D. So you could have ruled out, you could have either just picked these 2 or these 2. So you had a 50-50 chance of guessing. But we don't want to guess. We want to solve it. And we just did. Anyway, hopefully you enjoyed that. Let f be a real valued function defined on the interval from 0 to infinity. It does not include 0. And f is defined as the natural log of x plus the definite integral from 0 to x of the square root of 1 plus sine of t d of t. Then which of the following statements are true? And so more than one of these might be true. So let's figure them out. So A says the second derivative, there's two apostrophes here. The second derivative of f exists for all x between 0, or really all x greater than 0. Then they say the first derivative exists for all x greater than 0, and the derivative is continuous on that interval, but not differentiable. Okay, so everything they're doing, they're relating the function to the first derivative and the second derivative. So let's just figure those things out. So let's just write the function first. I'll just rewrite it here. The function f is equal to the natural log of x plus the definite integral from 0 to x of the square root of 1 plus sine of t dt. The derivative of f, so let me write it over here. So f prime of x is going to be equal to the derivative of this first term. Derivative of natural log of x is 1 over x. And then derivative of this, that's just the fundamental theorem of calculus, is going to be just this inside expression with respect to x as a function of x. So plus the square root of 1 plus sine of x. And now let's get the let's get the second derivative now. The second derivative, I'll do it over here. F prime prime of x is going to be equal to the derivative of this term. This is x to the negative 1. So it's going to be negative x to the negative 2, or negative 1 over x squared. That's negative x to the negative 2. You could view it that way. And then plus, so let's do the chain rule. What's the derivative of the inside? Derivative of 1 plus sine of x is cosine of x. So plus cosine of x times, now it's 1 plus sine of x to the 1/2. So it's going to be times 1/2 times 1 plus sine of x to the negative 1/2. So I took the derivatives. Now let's look at the choices. So the first choice says the second derivative of the function exists for all x greater than 0. If you're going between 0 and infinity and not including 0, that's essentially for all x greater than 0. Let's see if that is true. So over here, the one area, so this would be undefined if x is equal to 0, but that's not in the interval over here. Now let's see if there's, so let's just be clear. When you take something to the negative 1/2 power, let me rewrite it like this. I could rewrite it as, instead of writing to the negative 1/2 power, I can write it in the denominator as the square root of 1 plus sine of x. So if this denominator becomes undefined, the second derivative won't be undefined. So let's think about when that denominator might be undefined. So it'll be undefined if it equals 0. So 1 plus sine of x is equal to 0. Well, it's going to be equal to 0 if sine of x is equal to negative 1. If sine of x is equal to negative 1. And sine of x can equal negative 1 at x is equal to, let's see, if you go around the unit circle, sine is the y coordinate, so it has to go around. You could either go down, it would be negative 90 degrees, or positive 270 degrees. Or if in radians, if x is equal to, because we're assuming, or at least I'm assuming that we're dealing in radians here, if x is equal to 3 pi, if x is equal to 3 pi over 2, assuming we're in radians, that will make this undefined. So this f prime prime not defined at x is equal to 3 pi over 2, which is clearly in this interval. So choice A is false. Choice A does not work. Now let's see. Choice B says f prime of x exists for all x's greater than 0. Well, that seems to be the case. You can't put x equals 0, but that's not in the interval. And f prime is continuous on 0 to infinity. Yeah, it's continuous. No obvious discontinuities here. But not differentiable on 0 to infinity. Well, it's clearly not differentiable at 0 to infinity. The derivative does not exist when x is the derivative of the first derivative, or the second derivative, does not exist at x is equal to 3 pi over 2. We just saw that f prime of x is not differentiable at 3 pi over 2. So everything in this is true. Everything is true. It's not differentiable there because the second derivative is not defined at 3 pi over 2. Let's do part C now. Part C. There exists an alpha greater than 1 such that f prime, the magnitude, the absolute value of f prime of x is less than the absolute value of f of x for all x essentially greater than, for all x greater than that alpha. So let's think about this. Let's think about this a little bit. What we want to show is that beyond some threshold, the derivative is always going to be smaller than the original f of x. Or this is the derivative will always be smaller than f of x. So the first thing we might want to see, so let's just compare the parts that are comparable. So let's compare, first of all, the natural log of x. Let's compare the natural log of x to 1 over x. So when is, let's just set a threshold here. So is there a number, so at any number larger than that, the natural log of x is always going to be larger than 1 over x. And the number that pops into my head, just because it's an easy number to work with natural logs, is e. If so, for x is greater than e, it's pretty clear that the natural log of x is going to be greater than 1 over x. Think about it. At e, it's going to be evaluate to the natural log of e, which is 1. And 1 is clearly greater than 1 over e, right? E is 2.71, so on and so forth. So this is clearly true. And then as you get beyond e, as you get numbers larger than e, as this becomes e plus something, this number will become larger. And then this number over here will become smaller because we'll be dividing by a larger number. So it's clear that it exists just for this part, for the first part, the natural log of x beyond e. And we just have to find some threshold. That might not be the first threshold. But the natural log of x is definitely greater than 1 over x when x is greater than e. Now let's see if we can find a threshold for the second part. And if we can, then we can literally just pick the larger of the two thresholds, and then that will be a threshold above which f of x will always be larger than f prime of x. And to think about it, we just have to see that essentially this part of the function, let me write it this way. If I define this as h of x, this is h of x. This right here is h prime of x. H prime of x. We've already shown that for x is greater than e, h of x is greater than h prime of x. We've seen that already. Now let me define this over here. Let me define that as g of x. Let me call that g of x. And then this is its derivative. This is g prime of x. That is g prime of x. Now, let's just draw g of x. Let me draw g of x. Or let me draw g prime of x right over here. Let me draw it. It's actually a pretty straightforward graph to draw. So let me draw it over here. So when x is equal to 0, sine of 0 is 0 plus 1. You take the square root. So 0, 1, that's the first point. That is f of x equal to 1 when x is equal to 0. And then the next interesting point, maybe we'll take x is equal to pi over 2. So when x is pi over 2, sine of pi over 2 is 1. 1 plus 1 is 2. Take the square root. So it's going to be the square root of 2, which is someplace around here. So the square root of 2. And then let's just take when x is pi, sine of pi is 0. This becomes the square root of 1 again. So we're back over here. Then let's go to 3 pi over 2. Sine of 3 pi over 2 is negative 1. Negative 1 plus 1 is going to be 0. So we're going to be down here. And then we go again to 2 pi. To 2 pi. Sine of 2 pi is 0. 0, 0 plus 1 is 1. Take the square root. You're back over here. So this graph, g prime of x, we're calling it. This graph over here looks like this. It looks something like this. This is my best attempt at drawing it. It just keeps oscillating. At its maximum point is square root of 2. Its minimum point is 0. And it keeps oscillating. So this is g prime of x. G prime of x is equal to the square root of 1 plus sine of x. Now what is g of x? What is this thing over here? Well, this is the definite integral from 0 to x of this thing. So you take any x value. This thing over here, g of x, is the area. It's the area over here. So what's happening here? So let's think about this. As we get to larger and larger x values, the area gets bigger because this line never drops below the x-axis. So as we get larger and larger x values, this area just keeps getting bigger and bigger and bigger. So we can write g of x unbounded as x goes to infinity. G of x approaches infinity. What about g prime of x? G prime of x, it maxes out. It just keeps oscillating between 0 and square root of 2. So g prime of x max, or maybe I should write it this way, the max of g prime of x is equal to the square root of 2. So it's pretty clear that at some point this area is going to be, there's some x value where this area is going to be more than the square root of 2. Let's call that point alpha. And after that alpha, where maybe it's over here, I mean clearly we could say at x equals 10, we definitely have a lot of area under this curve. We definitely have, the area is definitely bigger than the square root of 2. So let me just write it there, because we just need to find some boundary. So let's just say at x greater than, I'm just picking an arbitrary number, at x greater than 10, it's clear that the integral from 0 to x of the square root of 1 plus sine of x or I should say 1 plus sine of t dt, it's clear that that is going to be greater than the square root of 1 plus sine of x. Because this is the area. At 10, this thing, at any value above 10, this thing at most can ever get to square root of 2. This thing's just going to keep growing and growing. And at 10, it's already going to be larger than the square root of 2. So we know that there's some boundary. So for x is greater than 10, so let's write it this place. So for x greater than 10, well, 10 is definitely greater than e. We know that h of x is greater than h prime of x. We know that's true. 10 is clearly greater than e, so we can state that. And we also know that g of x is greater than g prime of x. So we know that f of x, which is equal to h of x plus g of x, is going to be greater than f prime of x, which was the derivative, the sum of the derivative, which is equal to h prime of x plus g prime of x. So we know that this is true. We can make alpha equal 10, and this thing is going to be true. So this is true. Now let's do part D. There exists a beta greater than 0 such that the absolute value of f of x plus the absolute value of the derivative of f is going to be less than or equal to beta for all x. Well, we already know that f of x is unbounded. F of x is unbounded because this part of it, this integral part of it right here, just keeps increasing as x gets larger and larger and larger. It never dips below. We never have negative area. So this area just keeps growing. So this is unbounded. And actually, so is the natural log of x. The natural log of x is also going to be unbounded. So you cannot say that it's going to be less than some value, because it's going to approach infinity. So it's not going to be less than some value for all x greater than for all x from 0 to infinity. So you can't bound it. This is an unbounded function. Just this part alone is an unbounded function. F prime of x is. F prime of x, well, even there you have to be careful. But f of x is clearly unbounded, so this can't be true. There's not any kind of roof you can put on the as x. If you said, well, I think you get the general idea. So this is definitely not true. So the answer here is B and C.